Hello everyone. Today I'll be talking with you about the current of an inductor due to a force voltage. And so in this circuit here I have a ideal voltage source and it's imposing this voltage on our inductor here, and our main task is to find IL of t, which is the result of the current going through our inductor. So for t less than or equal to 0, Vs of t is 0. That is to say, Vs of t is off. For t greater than 0, Vs of t is 20 times t exponential negative 10t volts. That's our functional composition there for Vs of t. IL of t sub 0 is equal to 0. That is to say, there's no initial current flowing through this entire circuit. And then again, our task is to find IL of t for t greater than 0. Also, just as an extra note, we'll be using integration by parts in our derivation here. So to start with, we'll start with noticing that Vs of t equals VL of t. It has to, because that's the voltage imposed across our inductor there. And then what we'll take notice of is IL of t, which is directly what we're solving for, is equal to 1 over L between the limits of t and t sub 0, VL of alpha d alpha as integration variables, plus IL of t sub 0. Again, IL of t sub 0 is 0, so that'll come out as a term. We don't need to worry about that. And we'll go ahead and we'll make the appropriate substitutions here. So IL of t is going to be equal to 1 over L between t and t sub 0, and VL of t is equal to Vs of t. So now we can take and replace and put this function in place here, which we have 20 times, instead of t, we'll have alpha exponential negative 10 alpha d alpha. And we'll carry on our integration from there. This 20 is going to come out in front. It's a constant. It'll be 20 over L. 20 over L, our value of L, our inductance there, is 0.1. 20 over 0.1 is equal to 200. So we'll go ahead and we'll replace that there as a 200. So now our expression is IL of t equals 200 times t sub 0. We have alpha exponential negative 10 alpha d alpha. And so the next thing we'll take notice of is the fact that with this type of integrand, we're going to need to apply integration by parts. So I'm going to apply integration by parts by making, we're looking over here on the left hand side, u equal alpha. Then automatically du equals d alpha. Very simple. Next, I'm going to make dv equal the rest of everything else here, which is exponential negative 10 alpha d alpha. Then v equals the antiderivative of that, antiderivative of dv, which is going to be the antiderivative of exponential negative 10 alpha d alpha. What we get from that is negative 1 over 10 times exponential negative 10 alpha. That equals v. And so we're going to apply these substitutions here, and by applying these substitutions, we'll be able to integrate this function. So now IL of t is equal to 200 with our integration here. Well, 200 with u. What is u? It's going to be multiplied by all of that. U is equal to alpha We're going to be replacing that with t, because when we evaluate our function, it's going to come out to be in terms of t, and it's no longer being integrated. It's actually the end result. So we're going to put t here instead of alpha, and v is equal to -1/10 exponential -10, and then we have an argument of alpha, but instead we'll use t. That's going to be what v is, and then that's going to be subtracted from between the limits of t and t sub 0, v, which again is -1/10 exponential -10 alpha d alpha, because du is d alpha, and that's what we'll have here. And so now that we have that down, go ahead and erase this and carry on. And so IL of t is now equal to 200 times -t/10 exponential -10t, plus, we're going to bring this constant out in front, plus 1/10 integration here between t and t sub 0 exponential -10 alpha d alpha. So we have our 200 being multiplied by all of that, these two terms on the inside. So next what we'll do is we'll go ahead and we'll integrate this part of our whole entire expression here, this term. And so now IL of t is equal to 200 times -t/10 exponential -10t plus 1/10, and then when we integrate we get -1/10 times exponential -10 alpha between the limits of t and t sub 0. Next, IL of t equals 200 -t/10 exponential -10t. And then now what we have here is -10 times 10, that's 100. Negative minus times a positive is a negative, so 1/100 exponential, and that's evaluated between t and t sub 0, exponential -10t minus exponential -10t sub 0. Now, t sub 0 is usually our starting point. Say like if you had a graph, and this is in time, t sub 0 is usually at 0. So that's what we're going to assume here for simplicity. And so t sub 0 equals 0. So if t sub 0 equals 0, then at 0 times -10 is 0, and anything exponential raised to the power of 0 just simply equals 1. So we'll go ahead and we'll apply that here next. So now IL of t equals 200 -t/10 exponential -10t minus 1/100. We have exponential -10t minus 1. That's what we have up to this point. Go ahead and make some more room here, and we'll continue on. So now, IL of t equals 200 times negative t over 10 exponential negative 10t, and we'll apply and distribute that negative 1 over 100, so we get negative 1 over 100 exponential negative 10t plus 1 over 100. Because we have negative here, negative times a negative is a positive, and 1 over 100 times 1 is 1 over 100. So next what we'll do is we'll distribute inward our 200, and so that arrives us at IL of t equals 200 over 10 is equal to 20. So that'll be a 20. Then we distribute it over here. 200 over 100 will be simply 2. And the same thing here. So now what we have is IL of t equals negative t, negative 20t, negative 20t exponential negative 10t minus 2 exponential negative 10t plus 2. And if we go ahead and we rearrange that and put our positives in front, now what we have is IL of t equals 2 minus 20t exponential negative 10t minus 2 exponential negative 10t. Next, what we'll do is we'll factor out our exponential here, and so now we have IL of t equals 2 minus 20t when we factor out here, we'll bring out the negative 20t and the 2, so we'll have negative 20t minus 2 times exponential negative 10t. And so next, we'll bring out this negative in front, and so now IL of t is equal to 2 minus 20t plus 2 exponential negative 10t. So finally we got to an expression that is pretty much about as simplified as it can be. And we'll use this expression to compare what we get from our analysis in a circuit simulator. And so we'll compare that with a circuit simulator result and see whether or not this functional composition actually holds true. Of course, we'll make sure Vs of t, which is equal to 20 times t times exponential negative 10t, is also verified in our simulator. And we'll go ahead and do that that verification right now. Okay, so for our simulation verification here, what we'll do is we will make sure that we have our forced voltage composition here, which is 20 times t times exponential negative 10t, and we'll verify that. Go ahead and copy that expression. we will verify that up to this point in the circuit by placing a voltage probe here. So this is the forced voltage across our inductor, and our simulation gives us this. So we do have that, and let's confirm and match that up against our math expression that we have on the board. And in fact, it matches up at every point. The red, which is our math expression, overlays the green at every point on our graph, and so it's a perfect match. So we know that what we are subjecting our inductor to is in fact correct. So the inductor value here, again, we're going to confirm, make sure that it's what we had on the board is 100 millihenries or 0.1 henries, and we have an initial condition of 0, which means no current is flowing through this inductor initially. Now this resistor down here has a value of 1 nano ohm, and in order for the simulator to converge with the results, and in order for the simulator to work, you need to have a resistor in series with this inductor, or else you get an error, a simulation error. So this resistance is just basically a placeholder, and that's why I made the value so very small, so that it would basically minimize any effects that a series resistance would have. So next, for our resulting current, which is what we derived on the board, was 2 minus 20 times t plus 2 times exponential negative 10t. And we'll go ahead and we'll take our voltage probe off, and we will put on a current probe and see whether or not our current actually matches up. So our simulation gives us these results for our current that results from subjecting our inductor to that forced voltage. And now we're going to take a look at what we derived on the board, which is our math expression there, and see whether or not it actually matches up. And it does. In fact, it matches up at every point on the entire curve here. Again, our math expression is in the red, and it's overlaying the green, which is our simulation result. So at every point we have verification there. So that will do it for our simulation part of this video, where we've verified that what we have on the board is actually the case.
Thank you for watching this video. Hopefully it was helpful, and have a nice day.